Welcome back guys, this is Ashmin here. In this video we are going to solve the problem Count Luck. Ron and Hermione are deep in the forbidden forest collecting potion ingredients and they have managed to lose their way. The path out of the forest is blocked, so they must make their way to a portkey that will transport them back to Hogwarts. Consider the forest as an n cross m grid. Each cell is either empty, represented by dot, or blocked by a tree, represented by X. Ron and Hermione can move together inside a single cell, left, right, up, and down through empty cells, but they cannot travel through the tree cells. Their starting cell is marked with the character M, and the cell with the portkey is marked with a star. The upper left corner is indexed as 0, 0. So this is a zero based indexing graph. So all the things are considered as like a graph like structure because we are going to traverse inside the matrix. So here in this example M is here, and we are going to traverse this path to reach this portkey star. So in the example above, Ron and Hermione are located at index 2, 7 and the portkey is at 1, 2. Each cell is indexed according to matrix conventions. Hermione decides it's time to find the portkey and leave. They start along the path and each time they have to choose a direction. She waves her wand and it points to the correct direction. Ron is betting that she will have to wave her wand exactly k times. Can you determine if Ron's guesses are correct? So each time if they move in a particular direction means Hermione have to wave her wand, and they have specified that number of times k. If it is equal to k means we have to display the output. So here the map from above has been redrawn with the path indicated as a series where M is a starting point, 1 indicates a decision point, and 0 is just a step on the path. So here you can able to see, right, Hermione is here and she is moved along this direction and she waves her wand and she moves in the possible direction here, and again we have two directions here. So here there is a dot and here there is another dot will be there if I consider this example. So she has to wave her wand here, and again she follow the path, and when he reached this position again she has two directions, that is here and here. So she has to wave her wand, and again if you follow the path means we have reached the portkey. So if you consider this example, so there were the three instances marked with 1 where Hermione must use her wand. Note, it is guaranteed that there is only one path from the starting location to the portkey. So there is always a single path, and we just have to find the path and determine how many times Hermione waves her wand. So when we have to wave her wand, so whenever we have a decision point, like if I am considering this matrix as an example, so the M is the starting point, and if it goes along this direction, here we have two directions to take, right? This dot and this dot. So Hermione has to wave her wand, and in this direction if we follow the path means again here two directions are there. Now again here she has to wave her wand. Now again we are going in this path, and when we reach this position we have to go in either of these positions, right? So again she waves her wand, so we will follow this path. Finally we reach the portkey. So that's how the logic works. Let's see the constraints. So here we have multiple test cases, that is 10, and the constraint is up to 100, and k is also 10,000. So it is equal to k, that is the output. We have to print impressed if k is equal to the number of times Hermione waves her wand, or else we have to print oops. So that is our output we have to do. And again here you can able to see we have 3 examples and the explanations are given below. I will explain it now. So in the first example, this is the matrix and this is the starting point, and in the starting point you can able to see we have two directions to take. One is left direction or another one is down direction. So Hermione will wave her wand here itself, and we will go along the way to the left and we will find the port key. So here k is 1, so 1 equals 1 is true, we will say impressed. And here this is the same example as above, so that is 3. We already concluded that condition, so we will say impressed. And again here we have the same example, but the number of times Hermione waves her wand is 3, but here the k is 4, so we have to print oops because it not satisfies the condition. So I think overall you can able to understand the logic. Usually people would have missed this, like they can't able to interpret when she waves her wand. Just consider the adjacent cells. How many cells are there? If there is more than 2 means you have to wave her wand. But in this example you can able to see for the starting point, if they have more than one direction itself, that is if there are two directions in the starting point itself, you have to wave the wand at that point itself. So this is a corner case, I will cover it later. Now let's dive into the problem. Now I will define the row and column for the matrix. So R equals len of matrix and C equals len of matrix of 0. So this is the row and column. You can also use this n and m, but people are not considering the main function, so I'm just defining the row and column here. And after that we have to define count. So I will initialize a global variable count here outside the function, because we are going to go in that way, or else it will make the code somewhat complicated. That's how I have done that. So I will say global count if you want to use the count globally. So these are part of the initialization. And again here if you consider the matrix, these are all just a string. So this is not like a complete individual cells, they are just represented as a string like structure. So if you want to do some operations on the string, means we have to convert it into a matrix like structure. So convert strings into individual cells. So what I'm going to do is I'm going to iterate the matrix. So for I in range of R, now matrix of I equals list of matrix of I. So what it does is it will just split the string into individual characters and make it as a list, and I'm just assigning the list into the same row. So what it does is it will just make the string into mutable operations. So string is basically immutable, so that's why we are just doing this operation. Now after that we will go for the main function. So in the main function I am going to make one thing as flag. That means we have reached the destination. So flag equals false. So now I'm going to iterate the matrix. When we reach m, we will call the DFS function, that is depth first search. So this is like a graph algorithm, that's why I already mentioned that. So I'm going to use DFS here. So I'm going to traverse all the indices. So for I in range of R and for J in range of C, now we have to check for the condition. If matrix of I and J equals m, then we have to call for the function. So before calling the function, I am going to make this cell as passable. So I'm just going to make this as a dot. So let's do that. So matrix of I and j equals a dot. So instead of m, I'm just making it as a dot to make it as passable. And after that, I'm going to call the function. So flag equals dfs of I comma j, and I'm going to pass the matrix as well. So after calling this function, it will do all the operation, and after that we also increment these counts. So after this few operation needs to be done. I will cover that later. So now I am going to define the DFS. Def DFS of I comma j comma matrix. Now here also we are going to use that global, because this is like a function. You can also define this function outside this function we are calling, but I am going to define it right here. So here I am going to call that global count, so we can able to access this count variable globally. Now if matrix of I, so this is the base condition, I and j equals star, that means we have reached the end, we will return true. So that means we have reached the end. So this will be the flag variable if we return it, or else we will make the matrix as visited. So I already mentioned to make the matrix visited. So make the cell visited by placing 9. So matrix of I and j equals 9. So this will make the cell as visited, and it will try reaching the adjacent cells. Now we have to create a local flag variable. So flag, so this is just an indication of a boolean variable. I will make it as false as before. Now we have to go for the traversal. So for x comma y in zip of xi comma yi. So we usually do the iteration right, so we can able to go in top, bottom, left and right. So we have to define this xi and yi. So I will just define in the initialization part. So xi equals a list, yi equals another list. So here I am going to specify 0 comma 0, 1 comma minus 1, and here in yi 1 comma minus 1 and 0 comma 0. So this is all the possible four direction. Okay, 0 and 1 means it will go to the left, and 0 and minus 1 it will go to the right, and this is top, and this is so this is bottom, this is top. So like that it will go in all the four directions. Now here inside the loop we have to check whether it is in the range or not. So to check that, if 0 less than or equal to I plus x less than r, and 0 less than or equal to j plus y less than c, and so this is whether it is within the matrix range or not. So that is to check this condition, and after that we also need to check whether there is no tree at all. So matrix of I plus x and j plus y not equals x. So I'll just move it slightly so we can able to see it properly. So we have to check for the condition, right? Because we can able to move only in the dots. So it should not equal to x. And here also we will make this 9. Instead of that, I will just make it as v as a string. So I'll just make it as a string. Now here, if it satisfies this condition, I will call the same function again. So that will be flag equals dfs of I plus x j plus y comma matrix. So it will search for the path. After finding the path, if it is true means, so if flag equals true, or else we can able to say just flag itself, you can do anything you want. Now if it is true means I will change the cell back to 0. So matrix of I and j equals 0, and I have to increment the count when there is a neighbor greater than 2. In the other parts I already mentioned, if you are making a turn means if the adjacent cells are having 3 cells, that is more than 2 cells, means we will be incrementing the count by 1. So here I will say count plus equal to 1 if neighbor of I comma j is greater than 2, else it is 0. So this is the condition for placing the wand. Placing the wand, and after that we will return flag. Return flag. Here if it is completed means I will make the row again as visitable. So matrix of I and j equals dot. So before it is considered as visited, if you are completed the whole path means we have to change it back to the dot, and after that we will return the flag. Return flag. So now we have to define this function neighbor to check for the adjacent cells, like how many adjacent cells are possible to for us to move. That we have to find for this function, and here I will say make the cell passable again. So I think this completes our DFS. I will also print the matrix how it looks after finding the path, so you will get to know. So I will do it later. So far we have completed these functions. I think you just pause the video and try to trace it how this works. I will also give you a overview at the end. So now we will define this neighbor function here. So def neighbor, so that will be I comma j, I comma j, check for number of adjacent passable cells. So now here I am going to initialize a temporary count variable. So temp equals 0. Now here I am going to traverse. So this will be the same thing. I'll just copy this and paste it here. I'm just checking whether it is in the range or not, and this should be this is also same. It should be passable. If it is possible means we will say temp plus equals 1, and finally we will return temp. So that completes our function here. Now these all the functions are completed. Now after getting this thing, we will be having some count after finding the full path, and here we have to check for another corner case, that is check for source cell. As I already said, we have two corner cases. If you consider m means if it has more than one adjacent cell means we will be incrementing that count, but for other cells we will be incrementing by 2. So what we are going to do is we have to remove a cell for the source, so that we have changed here, right? For this dot we have to remove that one. So count minus equal to 1 if neighbor of I comma j greater than 2, else 0. Now after that again count plus equals 1 if neighbor of I comma j greater than 1, else 0. And after that I will just break this loop. Now why I am doing this operation here? Because in this m cell I am just replacing it by a normal cell. So when we are considering the normal cell, it will automatically increment the count if it has more than 3 adjacent cells. So let's consider the cell m. So for this m only, we have to check for the condition. If it is like greater than 1 itself means we have to increment that by 1. But we didn't handle that here. We just handled it as a normal cell. So that's why I'm just reversing the operation here. And after that I'm just doing the same operation for this m cell. Maybe if you just comment these part out and try to run this example, it will run it for sample case, but it will show some wrong answers for other test cases. So you will get to know if you understand the logic properly for the source cell and for the normal cell, how you have to calculate the adjacent cells. Now after doing this, we have to check for the count, right? Now here I am going to check if flag, that means if flag equals true and count equals k, I will return impressed, or else I will return oops, and it should have an exclamation mark, so I will place it here. I'll just run it once to see whether it is working fine or not. Showing some runtime error. Okay, I think it just reached the maximum recursion depth. For that you have to set some recursion limit. So I will say sys dot set recursion limit. I will say some couple of numbers. I think that will be enough. Python usually have a recursion limit of 1000. We have to change it if you are going to do this kind of graph or searching problem. Whenever we use this recursion, try to use this limit. Let's run the code again. Okay, that is too large of a number. I'll just remove few numbers. Let's run it again. Okay, here I have made an error. I didn't use a for loop here. Let's copy this for loop and paste it here and just move this. Okay, I have made a mistake here. So here this is like not equals to x. Instead of that, just change it to in. So it can able to allow dot dot and star, that is the destination. So I will try to squeeze it here. So these are the possible cells it can able to go, because we are making our cells as v, right? So it will go in a cycle because of this v. So if I just consider that is not equal to x, means it's not a suitable condition. So we have to specify here, and in the set recursion limit I'll just set it as 10 power 8. Okay, so the logic is actually right, but the count remains the same. That's why it's not working, because we having multiple test cases. So what I'm going to do is I'm going to initialize count equals 1 inside this function. Let's run it again. Now it passes all the test cases. Let's also see the matrix, how this works. So you can able to see, right, how the path is working. If it's not satisfying, means it's just reversing back and going into the other possible direction. That's how it is working. Maybe instead of printing here, maybe we will just print inside here. So we will just trace the zeros also. So I'm just taking my time, because this is like a complex problem. You have to understand how this works, so it will be very useful for your future problems. Okay, it's not very well. Yeah, now, so this is for the first problem. You can able to see it is visited, and when we reaches the final destination, it's actually making all the path as 0. And here for the second one, we are making all the things as v, and when it reaches the final destination, we are actually traversing backwards, like making it as 0 0 0 0 0, and we will get the final path here. You can able to clearly see, I guess the count is 3, and we also got the final path. So this is for the second one. So this is how it works. Now I will just remove these things. Let's quickly go through the problem once, so it will be the last. So initially I'm just making the count variable as 0, so we can able to access it anywhere inside the function. So these are some of the initialization step. So count equals 0, length of the matrices, and I'm just making the string into individual cells of matrix. And in the main function I'm just calling this dfs function when it reaches this m cell, and I'm just doing this operation as I already mentioned. For the m cell only, we have to check for this individual condition, like the neighbors are more than 1, means we have to increment the count. So this line is just to reverse the operation that we have done inside this function, that is inside this dfs. So when we call the dfs, we are going to initialize the base condition, that is if we reach the star, means we will return true, or else we will make the cell as visited and go through all the adjacent cells. So that will be mentioned here in xi and yi, and the possible paths are a dot or the star. So if it satisfies this condition, it will call the dfs again to the adjacent cell, and it will go through the function again and again until it reaches the destination. So when it reaches the destination and it is true, means we will make that as 0 to have a path. And while we backtracking the path, so this is actually backtracking the function. While we backtracking the path, I'm just checking the neighbors. If it is greater than 2, means I'm just incrementing the count by 1, and after that I'm just returning the flag. So if we check for all the possible paths in this particular cell, and if it is not reaching the destination, means we will make the cell passable again, and we will return the flag. So flag will obviously be false. So inside this flag is obviously true if it is reaches the destination. So that is returned here. So this will be true if it reaches the destination. If not, means this will contain false. And in the neighbors, I'm actually checking for the nearby cells, and I'm incrementing the temporary count by 1 if the adjacent cells are passable, like we can able to move into the adjacent cell. And finally, after doing all the operations, I'm just checking for flag. If it is true, means that is reached the destination, and count equals k means that satisfies our condition, and we will print impressed, or else we will return oops if it not satisfies this condition. So I think that's it, guys. This is like a bigger problem and much more complex. This is definitely not a medium problem, but they just defined it as a medium problem only. Okay, if you have any other logic other than this, means please leave a comment below. It will be very helpful for the community. Let's submit the code now. Yes, it passed all the test cases. If this logic and if the video is helpful to you, hit the like button and don't forget to subscribe the channel for future videos. Stay tuned for the next video.